Howdy, y'all. Welcome to the last video in this part 4 series for aviation weather, where we're talking about the heat imbalances in the Earth's atmosphere. So in this video specifically, we're going to be talking about the seasons and diurnal temperature variation. So I'm Dr. Andy Moltar. I'm a flight instructor, a CFI IIMEI. I'm a former corporate pilot, and I'm a professor of aviation, and one of the classes I've taught before is aviation weather. So you're getting a free aviation weather education watching on YouTube. So make sure to subscribe so that you get notified as I make more of these videos. All right, so the seasons are caused by the tilt of the Earth's rotational axis as the Earth orbits the sun. And the Earth, it's not just the equator that's closest to the sun. The Earth is actually tilted 23.5 degrees. And so this accounts for the changing hours of daylight throughout the year. If the Earth wasn't tilted, wherever you live at on Earth, you would receive the same amount of daylight in nighttime. But because the Earth is tilted 23.5 degrees, that's why we have changing daylight hours throughout the year. And so, as you can see at the autumnal and vernal equinox, that's when we are getting the same amount of daylight and nighttime throughout the year or throughout the day. And then as we move away from the equinox towards the solstices, then it changes. So during the winter solstice, and I'll give us a laser pointer. So during the winter solstice, you'll see that more of the southern hemisphere is exposed to sunlight than the northern hemisphere. And if you watch the last video, remember we were talking about the solar zenith angle. Because the southern hemisphere is receiving a lower solar zenith angle, it's receiving more heat energy, and therefore the southern hemisphere is going to be a bit hotter. And then during the winter for the northern hemisphere, less. So a lot, there's a portion here of the northern hemisphere that doesn't receive any solar radiation at all during the winter solstice. And for a part of the year, the North Pole doesn't receive any daylight whatsoever. So it's just dark 24 hours a day for a considerable amount of time. But the rest of the northern hemisphere does receive daylight, but a lot of it, it's a high solar zenith angle, and so there's less heat energy received per square mile. But then we go through half the year later. Now we're in the summer solstice, where now more of the northern hemisphere is exposed to the solar zenith angle, to the sun's heat energy through radiation, which we talked about in part 2. So here it's going to be hotter in the northern hemisphere and colder in the southern hemisphere. Now, a little question is, when is the Earth closer to the sun? Because it's not a perfect circle orbit of the Earth going around the sun. It's more like an elliptical, kind of like it's shown here. And so at what point is the Earth closest to the sun? Is it during December, or is it during the like June? Well, the Earth is actually closer to the sun in December. Now, if you're watching this and you live in the northern hemisphere, you're like, that doesn't make any sense because it's colder. Well, that's what we've been talking about in this whole video. Because we're pointed away, we have our tilt of the axis is 23.5 degrees away from the sun. Because we're receiving less heat energy, even though we're closer to the sun, the amount of radiation received is less per square mile, and so it gets colder. But if you live in the southern hemisphere, well, when the Earth is closest to the sun, you have less of a solar zenith angle, so therefore it is hotter. So the difference is about 3 million miles. So the average is about like 95 million miles, but we're about 3 million miles closer to the sun during December than we are during June. All right, then we have diurnal temperature variation. So diurnal just means day, night. So the diurnal temperature variation is the daytime maximum and the nighttime minimum of air temperature due to variations of insolation caused by the rising and setting sun as the Earth rotates around its axis. So basically, we're receiving solar radiation throughout the day when our side of the Earth is pointed, facing the sun. But at night, we're no longer receiving solar radiation because we're pointed away from the sun. But throughout the day and night, we're still experiencing terrestrial radiation where the Earth is releasing heat. And so in this picture on the top here, I'll give us a laser pointer again. So on the top here, you see at midnight, the Earth is losing heat. And so this red line represents temperature. And so we're losing heat through terrestrial radiation. And so at sunrise, you'll see that as we're getting solar radiation, we're still losing a little bit of heat until sunrise. And then we're finally facing the sun. And then it's going to start warming up because we're receiving solar radiation. We're receiving more solar radiation than we are losing heat through terrestrial radiation. And so we keep on receiving more and more solar radiation. So that's why at noon, it's not the hottest part of the day, is because we continue to receive more solar radiation at a faster rate than we're losing heat through terrestrial radiation. But then the Earth is still rotating, and we're starting to point more and more away from the sun. The solar zenith angle gets greater, so we're receiving less solar radiation. And then finally the sun sets, and then now it's only terrestrial radiation. So we were losing heat throughout the day through terrestrial radiation, but the solar radiation was so much that the temperature was increasing. So on the bottom picture here, it's just showing the same temperature change, but the sunrise, we're starting to receive that solar radiation. Even though this is the point where we receive the most solar radiation, the temperature is still climbing, but it's just we haven't absorbed as much solar radiation as we have until late afternoon, early evening. But then finally the sun goes down, and it's just outgoing terrestrial radiation that continues to go. All right, so this is part D, the fourth video in this part 4 series. And so if you haven't watched those, go back, make sure you subscribe so that you can get notified every time that I come out with a new aviation weather video or any other video on aviation. So after watching those videos, can you answer these questions? And if you haven't watched the videos, maybe you can answer these questions. What is the cause of Earth's weather? Well, that'd be unequal heating of the Earth's surface. All right, what is the relationship between solar radiation and terrestrial radiation? How do overcast layers affect surface temperatures at night? That's if you haven't watched my video, you probably don't know. So, can you describe latent heat? What's happening when water changes from, a liquid to a solid? Is it absorbing heat? Is it losing heat? Why is there a difference in surface temperatures with latitude? What causes seasonal changes in weather? So, if you haven't seen those videos, go back and watch them. And I know these videos are not the most exciting, but it's important because later we're going to be talking about some really complex weather topics. And without watching these previous videos and reading your aviation weather handbook, it makes learning those more complex topics more difficult to learn. So, all right. Well, if you have any questions, leave them in the comment section. I'll be happy to answer them. All right, y'all take care. Bye.